The Sun. The star at the center of the solar system is a massive, nearly perfect sphere of hot plasma that radiates energy from its surface, mainly as visible light and infrared radiation. It is the most important source of energy for life on Earth and has been a central subject for astronomical research since antiquity. We explore facts about our giant star, how it came to be, how it was observed and studied, its estimated humble demise, and how it will affect the solar system and, more especially, us living on Earth. So what did our ancestors think about the Sun? The Sun was originally thought as a supernatural entity and was believed to be the center of the planet's orbit in ancient cultures. Solar deities have played a significant role in various world religions and mythologies, including ancient Egyptians, Incas, and Aztecs. Ancient monuments, such as stone megaliths in Nabta Playa, Egypt, Menadra, Malta, and Stonehenge, accurately mark the summer or winter solstice. The ancient Sumerians believed that the sun was Utu, the god of justice and twin brother of Inanna, the queen of heaven. In ancient Egypt, the sun was worshipped as the god Ra, portrayed as a falcon-headed divinity surmounted by the solar disk and surrounded by a serpent. In the New Empire period, the sun became identified with the dung beetle. With the Greeks, the sun was Helios, carried by a chariot drawn by fiery horses. Apollo, the god of purity, healing crops and herds, later on was also attributed to be a sun god by the Greeks. From the reign of Elagabalus in the late Roman Empire, the sun's birthday was celebrated as Sol Invictus, literally unconquered sun, soon after the winter solstice, possibly antecedent to Christmas. In the Bible, Malachi Book 4 verse 2 mentions the Sun of Righteousness, sometimes translated as the Sun of Justice, which some Christians have interpreted as a reference to the Messiah. Babylonian astronomers observed the sun's motion along the ecliptic, which is now known to be due to Earth's elliptic orbit. Greek philosopher Anaxagoras proposed that the sun was a giant flaming ball of metal larger than the Peloponnesus, reflecting the sun's light. Ptolemy estimated the distance between the Earth and the sun as 1,210 times the radius of Earth in the 1st century AD. The theory that the sun is the center around which planets orbit was first proposed by Aristarchus of Samos in the 3rd century BC and later adopted by Seleucus of Seleucia. This view was developed in a more detailed mathematical model of a heliocentric system by Nicholas Copernicus in the 16th century. In 1666, Isaac Newton observed the sun's light using a prism, showing it is made up of light of many colors. William Herschel discovered infrared radiation beyond the red part of the solar spectrum in 1800. Ernest Rutherford proposed that the sun's energy could be maintained by an internal source of heat, while Albert Einstein provided the key insight with his mass-energy equivalence relation, E equals mc squared. Sir Arthur Eddington proposed that the sun's pressures and temperatures could produce a nuclear fusion reaction, merging hydrogen into helium nuclei, resulting in energy production from the net change in mass. The concept of fusion was developed in the 1930s by astrophysicists Subramanian Chandrasekhar and Hans Bethe, who calculated the details of the two main energy-producing nuclear reactions that power the sun. The list goes on and on about scientists and observers of the sun throughout the centuries. This was true until we were able to send rockets and satellites into space to bring our scientists and observers' hypothesis closer to being fact. NASA's Pioneers 6, 7, 8, and 9 were the first satellites designed for long-term observation of the sun from interplanetary space, orbiting the sun at a distance similar to Earth. These probes made detailed measurements of the solar wind and the solar magnetic field. In the 1970s, two Helios spacecraft and the Skylab Apollo telescope mount provided scientists with significant new data on solar wind and the solar corona. The Solar Maximum mission probes were launched in 1980 by NASA to observe gamma rays, X-rays, and UV radiation from solar flares during high solar activity and luminosity. Japan's Yohkoh satellite, launched in 1991, observed solar flares at X-ray wavelengths, allowing scientists to identify several different types of flares and demonstrate that the corona away from regions of peak activity was much more dynamic and active than previously thought. The Solar and Heliospheric Observatory, SOHO, jointly built by the European Space Agency and NASA, was launched on the 2nd of December 1995 and remains in operation as of today. SOHO has provided a constant view of the Sun at many wavelengths since its launch, and has enabled the discovery of a large number of comets, mostly tiny sun-grazing comets that incinerate as they pass the Sun. All these satellites have observed the Sun from the plane of the ecliptic, so they have only observed its equatorial regions in detail. The Ulysses probe, launched in 1990, studied the Sun's polar regions and found that the solar wind from high latitudes was moving at about 750 kilometers per second, which was slower than expected. It is observed and calculated that the Sun today is halfway through its main sequence portion of its life, with no significant changes in over 4 billion years. It formed about 4.6 billion years ago from the collapse of part of a giant molecular cloud consisting mostly of hydrogen and helium, which likely gave birth to many other stars. This age is consistent with the radiometric date of the oldest solar system material, at 4.6 billion years ago. Astronomical studies reveal traces of stable daughter nuclei of short-lived isotopes, such as iron-60, that form only in exploding short-lived stars. A shock wave from a nearby supernova would have triggered the formation of the Sun by compressing the matter within the molecular cloud and causing certain regions to collapse under their own gravity. As one fragment of the cloud collapsed, it began to rotate due to conservation of angular momentum and heat up with the increasing pressure. Much of the mass became concentrated in the center, while the rest flattened out into a disk that would become the planets and other solar system bodies. The Sun is about halfway through its main sequence stage, during which nuclear fusion reactions in its core fuse hydrogen into helium. Each second, more than 4 billion kilograms of matter are converted into energy within the Sun's core, producing neutrinos and solar radiation. At this rate, the Sun has converted around 100 times the mass of Earth into energy, about 0.03% of the total mass of the Sun. During its time on the main sequence, the Sun is gradually becoming hotter in its core, hotter at the surface, larger in radius, and more luminous. This expansion in radius and temperature increased due to the helium atoms in the core, resulting in less thermal pressure. The Sun will eventually deplete liquid water from Earth in approximately 1 billion years, leading to a mass extinction. The Sun's luminosity will increase as it runs out of hydrogen in its core, causing it to expand over the next billion years. This expansion will occur first into a subgiant and then into a red giant. The heating due to gravitational contraction will also lead to hydrogen fusion in a shell outside the core, contributing to the increased luminosity. When the Sun enters its red giant branch phase, it will engulf Mercury and Venus, causing Earth's orbit to shrink due to tidal forces. By the time the Sun reaches the tip of the red giant branch, it will be about 256 times larger than it is today, with a radius of 1.19 astronomical units. The Sun will spend around 1 billion years in the red giant branch and lose around a third of its mass. After the red giant branch, the Sun has approximately 120 million years of active life left. The core ignites violently in the helium flash, converting 40% of the Sun's mass into carbon. The Sun shrinks to around 10 times its current size and 50 times its luminosity. After about 20 million years on the early asymptotic giant branch, the Sun becomes increasingly unstable, with rapid mass loss and thermal pulses increasing its size and luminosity. The Sun's maximum asymptotic giant branch radius will not be as large as its tip red giant branch maximum. The Sun undergoes a process of mass loss, resulting in a planetary nebula. This process occurs when the Sun loses its outer envelope and begins to form a planetary nebula. The ejected half of the Sun's mass becomes ionized into a planetary nebula as the exposed core reaches 30,000 Kelvin. The final naked core, a white dwarf, contains an estimated 54.05% of the Sun's present-day mass. The planetary nebula disperses in 10,000 years, while the white dwarf survives for trillions of years before fading into a hypothetical super-dense black dwarf, giving off no more energy. But this begs us to ask the question, what happens to Earth and humankind when the Sun disappears today? Imagine waking up one morning and the Sun just doesn't rise. What if, in an instant, our source of light and energy vanished? How long could we survive? What would happen to our planet? First off, let's consider the initial impact. If the Sun were to just disappear, the first 8 minutes after it disappears, life on Earth would continue as normal. That's how long it takes for sunlight to reach us. But once that last ray fades, darkness falls. Cities, forests, and oceans would plunge into a cold abyss. So, what happens next? Without the Sun's heat, Earth's temperature would begin to plummet. In just 1 week, temperatures would drop to about 0 degrees Fahrenheit. Within a year, most of the planet would be around minus 100 degrees Fahrenheit. And what happens to our oceans? As the surface freezes over, beneath that layer, the water would remain liquid for a time, maintaining some bizarre habitats. But ultimately, without sunlight, marine life would collapse as well. On land, plants would die off rapidly, causing a domino effect throughout the food chain. Animals and humans would struggle to find sustenance. But that's not all. The darkness would bring an unexpected beauty. The night sky would be unlike anything we've ever seen. With no light pollution and the Sun gone, we'd witness countless stars, galaxies, and cosmic wonders. With a chilling atmosphere, ice would cover the Earth's surface, and atmospheric pressure would eventually decrease, altering the very air we breathe. Oxygen levels would drop, making survival even tougher. Only those living in geothermal hotspots or underground could maintain some form of life. And as if that weren't enough, years down the line, our planet would turn into a frozen wasteland. A world where human civilization as we know it ceases to exist. Think of the stories, the history, the evolution, all lost in an eternal winter. So, could humans even survive? We'd need to adapt quickly. Some estimates suggest that humanity could retreat into underground cities or thermal shelters to escape the cold. Advanced technologies would be necessary to fend off the extreme temperatures, and we'd rely heavily on artificial and geothermal energy. And what about our place in the universe? With no sun, Earth would drift off, potentially colliding with another celestial body over time. It's a grim reminder of how interconnected we truly are with our solar neighborhood. So what can we take away from all this? The Sun is not just a glowing ball of gas in the sky. It's our lifeline. It sustains us, nurtures our ecosystems, and keeps our planet warm. And perhaps our ancestors were right. The Sun is a god, an inanimate being out there in space giving us life and allows us to exist, and at a blink of an eye can take it all away. If you enjoyed this video, please don't forget to like and share it. Hit that notification bell to see new videos like this. And remember to subscribe to Why on YouTube.